Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. In the previous module, we have seen the Doppler effect, why the Doppler effect arises and how to calculate the Doppler effect. Now let us examine what is the impact of the Doppler effect on wireless communication or the wireless channel. So let us look at the impact let us look at the impact of the Doppler on the wireless channel, and for that recall that the wireless channel coefficient is defined as the, or fading coefficient recall that our fading coefficient h is defined as summation I equal to 0 to L minus I AI e power minus j 2 pi f c tau I. Recall that the fading coefficient is defined as h is equal to I equals 0 to L minus 1 AI e raised to minus j 2 pi f c tau I, where f c is the carrier frequency. Alright. So, this is the definition of the fading channel coefficient h, flat fading channel coefficient h. Now, consider the ith path. When I look at the ith path and when I look at the mobile, so let us say this is my base station and I have my mobile which is moving at an angle of theta, and the ith path which has, so this is my mobile which is moving with a velocity of v at an angle theta. Now, if I look at the distance between the base station and the mobile, this is decreasing. The distance between the mobile and the base station is decreasing, right. As the mobile is moving at an angle of theta, the distance between the base station and the mobile is decreasing. Well, if the angle theta is between 0 and pi by 2, the distance is decreasing, and if the angle theta is between pi by 2 and pi, the distance is increasing. So, basically the distance is changing. As the distance is changing, the corresponding delay of the wireless signal, that is tau I, because remember tau I is the propagation delay. As the distance is changing, the corresponding propagation delay is also changing. Now, how is the propagation delay tau I changing? For that, let us look at this expression. Therefore, the corresponding delay tau I is now, how fast is this changing? So, if I write tau I of t, remember tau I is a function of the distance. So, it is equal to tau I minus, for a given time t, the distance is decreasing by v cosine theta t, right, and therefore, the time or the delay is decreasing by v cosine theta t divided by c. If you look at this figure, you will realize that the component of velocity in the direction of the base station is v cosine theta. Therefore, for a given time t, the distance in the direction of the base station is decreasing as v cosine theta t, and as a result the delay is decreasing as v cosine theta t divided by c. Therefore, what we have is that the net delay tau I as a function of t is decreasing as tau I, the initial delay, minus v cosine theta t divided by c. Now, if I substitute this in my expression for h, I have h equals summation I equal to 0 to L minus 1 AI e to the power of minus j 2 pi f c. Now, the delay is changing, which is tau I minus v cosine theta t divided by c. This can be further simplified as summation I equal to 0 to L minus 1 AI e to the power of minus j 2 pi f c tau I times e to the power of j 2 pi f c v cosine theta divided by c times t. But now, if you look at this component f c v cosine theta divided by c, if you look at this part f c v cosine theta divided by c, this is nothing but the Doppler frequency f d. Therefore, we can simplify h as h equal to I equal to 0 to L minus 1 a I e to the power of minus j 2 pi f c tau I times e to the power of j 2 pi f d t, where this f d equals the Doppler frequency. So, this quantity f d is the Doppler frequency of the system. Further, now you can see this component e to the power of j 2 pi f d t is a function of time. So, it is varying with time, and therefore, as a result the coefficient h is now a function of time, or is it? It is varying with time. Thus, as a result of this, observe that this factor e to the power of j 2 pi f t d, this is changing with respect to therefore, as a result our channel coefficient h is time varying. Such a channel coefficient h, which is time varying, is also known as a time selective channel. Since this coefficient h is varying with time, the wireless channel is known as a time selective channel. Such a time varying channel is also known as a time selective channel. Therefore, what is the reason for this time selective channel? That is because of the Doppler. Therefore, what is happening in this scenario, because of mobility, that is because of the mobile nature, because the user is moving, so this mobility is giving rise to Doppler. This Doppler is resulting in a time varying channel, and therefore, this time varying channel, this is a time selective channel. So, the mobility results in the Doppler effect. The Doppler effect is resulting in the time varying phase or the time varying channel, and this is therefore a time selective wireless channel. So, this Doppler effect is leading to the variation of the wireless channel with respect to time. Now, how fast or how slow is this channel changing with respect to time? For that, let us look at the phase factor. Consider the typical consider the phase factor. e to the power of j 2 pi f d t. Now, at t equal to 0, the phase equals j 2 pi f d times 0. So, it is 0. At t equals 1 by 4 f d, the phase equals 2 pi f d times 1 by 4 f d, which is equal to pi by 2. So, therefore, the phase has changed significantly from t equal to 0 to t equal to 1 by 4 d. Therefore, we can consider that this channel coefficient has changed significantly from t equals 0 to t equals 1 by 4 f d. Therefore, we can say that the channel has changed. One can say that the channel has changed significantly from t equal to 0 to t equal to 1 by 4 f d. So, in this interval of duration between 0 to 1 by 4 f d, or this interval of duration 1 by 4 f d, the channel has changed significantly. This can be defined as the coherence time of the channel. So, coherence time T c equals 1 by 4 f d. This is the definition of the coherence time. This is termed as the coherence time. So, the channel is changing significantly during the coherence time interval. So, we can say channel changes significantly during the coherence time T c, or another way to say this is that the channel is approximately so we can say that the channel is changing significantly during one coherence time interval, that is T c equal to 1 by 4 f d, or the channel is approximately constant for one coherence time interval, that is T c equals 1 by 4 f d. Okay. So, let us remember, and this is an important principle to remember, that the coherence time T c equals 1 by 4 f d. This is the coherence time T c. And let us, to understand this further, let us do a simple example to understand the concept of coherence time. For instance, let us do a simple example for the coherence time. Consider, as in the previous example, our Doppler shift equals 143 hertz, right, in the previous example. What is the coherence time T c for this scenario? We have seen that T c equals 1 by 4 f d equals 1 by 4 into 143 hertz, which is equal to 1.7 milliseconds. So, the coherence time for this scenario is T c equals 1.7 milliseconds. The coherence time is of the order of milliseconds. The coherence time for this scenario is roughly 1.7 milliseconds, which means that the channel is constant for 1.7 milliseconds approximately, and the channel is changing after every duration or after every slot of 1.7 milliseconds. So, the way to interpret this is channel is approximately constant (1.7 milliseconds), or channel is changing after 1.7 milliseconds. So, there are two ways to look at it. The coherence time is 1.7 milliseconds for this scenario with a Doppler of 1.143 hertz, which means that the channel is approximately constant for a duration of the coherence time, that is 1.7 milliseconds, or the channel is changing after the duration of 1.7 milliseconds. Therefore, the channel is a time varying channel. Alright. So, this concludes our characterization of our wireless channel in terms of the coherence time. Thank you very much.